Welcome to the introduction of basic operation and troubleshooting for the Caterpillar HI300 HEUI Fuel System. This presentation is a generalized introduction of the features, system operation, and troubleshooting basics for the HEUI HI300 fuel system used on the Caterpillar 3126B engine family. This presentation is not intended to replace the Caterpillar Service Manual or other service publications. For detailed troubleshooting information, always refer to the latest service publications. The HEUI fuel system has been used on the 3126 engine family since its introduction in 1995. The HEUI system provides high injection pressures, variable injection pressure at any engine speed, and full authority electronic control for optimal engine performance, fuel economy, and exhaust emissions. The HI300 refers to an inline, hydraulically actuated injector capable of delivering 300 cubic millimeters of fuel per stroke. This presentation covers 4 topics: a brief introduction to the 3126B engine family, the operation of the HEUI HI300 fuel system, the operation of the electronic control system, and finally, basic fuel system troubleshooting. Since its introduction in 1995, the HEUI fuel system has undergone many design changes to add features and improve performance and reliability. However, the operation and troubleshooting of all HEUI systems are very similar. This presentation uses a generalized example of a system with the latest features. The 3126 engine is a 7.2-liter displacement, medium-duty diesel engine which is used in a variety of truck and marine applications. The 3126B incorporates many features of Caterpillar heavy-duty diesel engines. 2 major features of this engine are the HEUI HI300 fuel system and full authority Atom 2000 electronics. The HEUI fuel system has a peak injection pressure of up to 23,500 psi or 162 megapascals. This high pressure atomizes the fuel into smaller droplets, which allows more complete combustion and reduced exhaust emissions. The 3126B is also the first Caterpillar medium-duty engine to offer injection rate shaping. This feature splits each fuel injection into 2 separate injections. The first injection is smaller and is called the pilot injection. It establishes a flame front for the larger main injection which follows. This feature reduces combustion noise by over 50% and significantly reduces nitric oxide exhaust emissions. The HEUI fuel system and electronics are completely adjustment-free. Most changes to engine horsepower or performance characteristics are accomplished by installing new electronic software or upgraded mechanical components. To repair the system, first identify and then replace the faulty component. All system components can be replaced quickly and easily by the dealer, including the injectors, electronic sensors, harnesses, connectors, and the electronic control module. This allows faster repair times and eliminates the need to rely on the fuel system repair shop to make component repairs and adjustments. The 3126B uses the exclusive Atom 2000 electronic control system. This system incorporates an electronic control module with a 32-bit, 24 MHz processor. This ECM has the speed and memory to allow electronic integration of engine, transmission, and anti-lock brake systems, as well as additional customer features. The Atom 2000 ECM also incorporates a J1939 communications data link. This data link is faster and has more capacity to allow electronic integration between the engine and other vehicle systems. Basic features of the Atom 2000 system include cruise control and soft cruise, vehicle speed limiting, electronic PTO functions, engine monitoring, exhaust brake control, idle shutdown timer, password protection, fast idle control, and theft deterrent. Additional standard features on the 3126B are parameter lockout for additional security. Key parameters will require a factory password to prevent field tampering. ECM fan control for applications with an on-off cooling fan. Full PTO functions, including programmable PTO throttle advance, PTO throttle limit, and PTO disengagement above a selected vehicle speed limit. A progressive shift feature that allows the customer to program both hard and soft engine speed limits during upshift to improve fuel economy. And finally, monitoring based on coolant level. In the event of low coolant level, the customer can choose several options, including a warning light only, a warning light and engine derate, and a warning light, derate, and engine shutdown. The operation of the HEUI fuel system is completely different from that of mechanically actuated fuel systems. If you're going to troubleshoot a HEUI system, you must have a basic understanding of how it works. In order to help you learn the basics of the HEUI system, we'll first discuss each system component, and then we'll show how these components work together. The HEUI fuel system consists of 7 major components. HEUI injectors use engine oil pressurized to 3,500 psi or 24 megapascals to produce fuel injection pressures of up to 23,500 psi or 162 megapascals and fire up to 19 times per second at rated speed. The hydraulic pump uses some of the engine's lube oil flow to generate the high-pressure oil needed to power the HEUI injectors. The injection actuation pressure control valve regulates pump outlet pressure by returning excess flow to the engine oil sump. The fuel transfer pump draws fuel from the fuel tank, pressurizes it to 65 psi, and supplies it to the injectors. The ECM is a powerful computer which controls all major engine functions. Sensors are electronic devices which monitor engine performance parameters such as pressure, temperature, or speed and supply this information to the ECM by means of a signal voltage. Actuators are electronic devices which use electrical currents from the ECM to perform work or to change engine performance. 2 examples of actuators are the injector solenoid and the injection actuation pressure control valve. Now that we've introduced the major system components, let's discuss the operation of each component in more detail. We'll start with the mechanical components and then cover the electronic components. Diesel fuel systems use a plunger and barrel to pump high-pressure fuel into the combustion chamber. Most fuel systems use mechanical means to power the plunger, such as cam lobes or rocker arms. But the HEUI system uses engine oil, pressurized to 3,500 psi to power the plunger, making the HEUI much different to troubleshoot than mechanically actuated fuel systems. The term HEUI stands for hydraulically actuated, electronically controlled unit injector. The injector is mounted in an injector bore in the cylinder head, which has an integral fuel supply passage. On older 3116 and 3126 engines, the injector seated on a brass sleeve that was swaged into the bottom of the injector bore. The brass sleeve provided a combustion seal and separated the injector from engine coolant in the water jacket. On 3126B engines, an improved stainless steel sleeve is used. This sleeve also separates the injector from engine coolant but the injector nozzle case seats directly on the cylinder head to provide a more positive combustion gas seal. The sleeve is installed with a light press fit and O-rings rather than the mechanical swaging used on brass sleeves. Increased wall thickness on the stainless steel sleeve allows the use of a simple puller tool to make sleeve installation and removal much easier. Actuation refers to the type of force used to power the plunger and pump the fuel out of the injector. Mechanically actuated fuel systems use a mechanical camshaft lobe to provide the force to pump the fuel. The HEUI injector uses engine lube oil, pressurized in a range from 870 psi to 3,500 psi to pump fuel from the injector. The HEUI injector works like a hydraulic cylinder, multiplying the force of the high-pressure oil to produce very high fuel injection pressure. This multiplication is achieved by applying the force of the high-pressure oil to a piston that is about 6 times larger than the plunger. The piston pushes on the plunger, pressurizing the fuel under the plunger. The pressure of the lube oil is called actuation oil pressure because it determines the pressure at which fuel will be released from the injector. Fuel injection pressure is about 6 times greater than actuation oil pressure. A low actuation pressure generates a low fuel injection pressure. Low injection pressures are good for low-speed conditions, such as idle and startup. For example, at idle, 900 psi of actuation pressure produces about 5,400 psi of fuel injection pressure. A high actuation oil pressure will result in high fuel injection pressure, giving better throttle response and reducing exhaust emissions. For example, under load or acceleration, 3,500 psi of actuation pressure produces about 23,500 psi of fuel injection pressure. In many operating conditions, the desired injection pressure is between the minimum and maximum. The HEUI system provides infinite control of injection pressure in this range, regardless of engine speed. This flexibility creates many performance advantages, such as improved responsiveness, greater economy, and reduced emissions. The hydraulic pump is located at the left front corner of the engine. It's a gear-driven, fixed displacement, axial piston pump. The hydraulic pump takes a portion of the engine lube oil and pressurizes it to actuation pressure to power the HEUI injectors. The top portion of the hydraulic pump is called the reservoir. It provides oil to the hydraulic pump during cranking until oil flow from the engine lube pump is established. The injection actuation pressure, or IAP, control valve is located on the side of the hydraulic pump. It controls pump outlet pressure by returning excess pump flow back to the engine oil sump. Because the pump must be sized to meet maximum flow requirements, it produces more flow than is necessary for most normal operating conditions. The IAP control valve is a high-precision valve that controls actual actuation pressure very closely. The ECM performance maps contain a desired actuation pressure for every engine operating condition. The ECM sends a control current to the IAP valve, which works to make the actual actuation pressure match the desired actuation pressure. If actual pressure does not match desired pressure, the ECM will increase or decrease the control current to the IAP valve to adjust the actual pressure. The IAP control valve is an actuator, since it converts an electrical signal from the ECM to mechanical control of an internal spool valve to control pump outlet pressure. The injection actuation pressure, or IAP sensor, is connected to the high-pressure oil passage that supplies actuation oil to power the injectors. The IAP sensor reads actuation pressure and sends a continuous signal voltage back to the ECM, allowing the ECM to know what the actuation pressure is at all times. The ECM is located on the left rear side of the engine. This powerful computer provides total electronic control of engine performance. The ECM uses engine performance data gathered by several sensors to make adjustments to fuel delivery, injection pressure, and injection timing. The ECM contains programmed performance software to define horsepower, torque curves, and all other aspects of engine performance. This software is known as the personality module. Some engines use ECMs with a replaceable computer chip that has the software already installed. The 3126 does not have a replaceable personality module chip. Its personality module is a permanent part of the ECM that can be reprogrammed using the flash feature of the Electronic Technician Service Tool, or ET. The ECM also logs performance faults and has the ability to run several automatic diagnostic tests when used with ET. The fuel transfer pump mounts on the back of the hydraulic pump and is used to draw fuel from the fuel tank, pressurize it to 65 psi, and supply it to the HEUI injectors. This pump is a spring-loaded single-piston pump operated by an eccentric on the back of the hydraulic pump shaft. The fuel transfer pump has two check valves. The inlet check opens to allow fuel from the tank to enter the pump and closes to prevent supply fuel from leaking back to the tank. The outlet check opens to supply fuel to the fuel supply passage in the cylinder head, which feeds the HEUI injectors. The outlet check closes to prevent pressurized supply fuel from leaking back through the pump. The HEUI injector completes an injection cycle more than 500 million times during its normal wear life. The ability of the injector to function properly after hundreds of millions of cycles requires more than quality design and manufacturing. This level of durability requires proper fuel filtration to remove microscopic abrasive particles contained in the fuel. Abrasive particles smaller than 10 microns in diameter can cause accelerated wear in any high-pressure fuel system. That is why much finer filtration is being used on modern engines with high-pressure fuel systems. The difference between normal wear and excessive wear on a plunger illustrates the importance of proper filtration. On the left, you see a plunger with normal wear after extended use. Notice the condition of the leading edge of the plunger, which is the highest wear area. The plunger on the right has suffered premature wear from excessive abrasives in the fuel. The damage to the leading edge of the plunger is due to large amounts of very small abrasive particles in the fuel being caught in the working clearance between the plunger and barrel. The wear shown here is the beginning of progressive damage that will eventually affect the entire engaged length of the plunger. This damage will allow significant fuel leakage between the plunger and barrel during injection. This leakage results in low fuel delivery into the cylinder and a symptom of a weak or dead cylinder. In short, a prematurely worn injector. This condition can be avoided using proper filtration. Caterpillar offers high-efficiency fuel filters that meet the demands of newer high-pressure fuel systems and specifies the use of high-efficiency filters on all new engines. Field experience demonstrates that these new filters more than double wear life of both new and old fuel systems over the previous standard 10-micron cat fuel filter. There's a good deal of confusion regarding filter ratings. One of the more common terms, micron rating, can be misleading. There may be significant differences in the ability of different brand filters with the same micron rating to remove very small abrasives from the fuel. Filter efficiency is commonly expressed in terms of nominal or absolute ratings. For example, A 5-micron nominal filter may only stop 50% of the 5-micron or larger particles striking it. In other words, every other 5-micron particle may pass through a filter with a nominal rating. Caterpillar high-efficiency filters are a 2-micron absolute rating, which remove more than 98% of particles 2 microns and larger. However, the rating of the filter paper means nothing if the construction integrity of the filter is faulty. In some cases, competitive brand filters, constructed with leak paths, allow large amounts of all size particles to pass. Why is this fine filtration important? A recent study by a noted independent research agency confirmed that abrasive particles 5 to 7 microns in size cause most abrasive wear in fuel systems. These very fine measurements can be difficult to comprehend. The diagram illustrates the relative size between a single micron and a human hair, which is about 80 microns, or 35/10,000ths of an inch. The smallest particle visible to the naked eye, such as a speck of dust, is 40 microns. Particles as small as only a few microns can cause significant injector wear due to the extremely high injection pressures. This example shows the difference in efficiency between a Caterpillar high-efficiency filter and a typical 5-micron nominal filter. The CAT filter removes more than 98% of the 5 to 7 micron abrasive particles in the fuel. The 5-micron nominal filter only removes about half of these particles. This is assuming the nominal filter contains no leak paths, allowing abrasives to flow around the filter paper. Over time, the additional abrasives cause accelerated wear in any fuel system. This includes pump and line systems that operate at significantly lower pressures than HEUI. Accelerated wear is more pronounced when the fuel contains unusually large amounts of contaminants. A good example of this problem occurred several years ago in a logging application. The customer operated log skidders with pump and lines fuel systems and complained that the fuel injection pumps were wearing out in as little as 2,000 hours. Subsequent investigation revealed no manufacturing defects, so abrasives in the fuel were suspected. The customer was using the standard Caterpillar 15-micron filter, so many of the abrasives reaching the fuel system were smaller than 15 microns. Testing the theory, which states very small abrasives are at fault, a side-by-side test was run with completely rebuilt pumps on the two identical machines. One machine remained equipped with the standard 15-micron filter, while the other machine was equipped with the high-efficiency 2-micron filter. Instead of changing filters at the recommended 250-hour change interval, both machines were run to 1,000 hours to see if the finer filter would plug from extended use. It didn't. After 2,000 hours of use, both pumps were disassembled and inspected. The pump using the 15-micron filter suffered significant abrasive wear, while the one using the high-efficiency filter looked and performed like new. These findings led to the testing of the high-efficiency filter in other severe applications around the world. In some countries, fuel lubricity is poor, and the fuel is loaded with very small abrasive particles. In these severe applications, the average life of many unit injectors in excavators has been about 1,500 hours. In extreme cases, injectors have worn out in as little as 200 hours. Since the introduction of high-efficiency filters in these applications, there has not been a single case of a documented system wear-out. Follow-up investigation shows some former problem machines now have over 5,000 hours of operation with no sign of injector wear. There are many other examples of dramatic improvements in fuel system life using high-efficiency filters. The improvements have been so significant that this filter is now the standard fuel filter for all Caterpillar products. Industrial or marine applications, where large amounts of water may be in the fuel, may have water separators in place of the primary fuel filter. The use and regular maintenance of a water separator is highly recommended where water contamination of fuel is a common problem. Water contamination is not usually as big a problem in mid-range truck applications that use fuel from reputable truck stops with very high fuel turnover rates. It is more of a problem for applications fueling out of stationary tanks with lower turnover rates. Fuel stored for prolonged periods has a much greater probability of generating condensation. The number one cause of injector failure due to plunger seizure is ingestion of large quantities of water in the fuel. All diesel fuel contains some dissolved water, normally about 0.1% by volume. We're not talking about this quantity of water. We're talking about large concentrations, in pints, quarts, or gallons, generated from condensation or tank leakage. The film strength of the diesel fuel separates the metal surfaces of the injector plunger and barrel. When the film is penetrated, metal-to-metal contact occurs between the plunger and barrel, resulting in plunger seizure and injector failure. Water has a much lower film strength than diesel fuel. Large quantities of water provide very poor plunger lubrication and film strength. When the weak film of water is penetrated, metal-to-metal contact occurs, leading to progressive damage and eventual injector failure. Some manufacturers of aftermarket combination fuel filters and water separators recommend removing or bypassing the factory-installed secondary fuel filter. Removing or bypassing the 2-micron secondary filter is not recommended by Caterpillar. The use of aftermarket filters, the use of competitive brand filters, or even bypassing the factory secondary filter does not void the engine warranty. However, the warranty on fuel system components does not cover abrasive wear from improper filtration unless a defect in material or workmanship is found in the fuel system component. Over time, abrasives in fluids can cause significant wear to even the most durable objects. Proper filtration is an essential factor in the life of all fuel system components. The injection actuation system takes lube oil from the main oil gallery and pressurizes it to power the HEUI injectors. This system takes the place of the gear train, camshaft, and rocker arms used to power mechanically actuated unit injectors. The injection actuation system has two main functions. It supplies high-pressure oil to power the HEUI injectors, and it controls the injection pressure produced by the injectors by changing oil actuation pressure. The injection actuation system has 5 basic components. The engine lube pump takes lube oil from the sump and pressurizes it to about 40 psi. The pressurized lube oil fills the engine lube circuit and provides supply oil to the hydraulic pump that powers the HEUI injectors. The engine oil filter removes soot and abrasive contaminants from the engine oil to prevent damage to critical engine components such as bearings and piston rings. The hydraulic pump pressurizes engine lube oil from 40 psi to between 870 psi and 3,500 psi to power the HEUI injectors. The IAP control valve returns excess flow from the hydraulic pump to the sump in order to control pump outlet pressure. The IAP sensor detects actuation pressure present at the HEUI injectors and sends a signal voltage back to the ECM. This tells the ECM what actual actuation pressure is at all times. Now, let's look at the path of oil flow through the actuation oil circuit. Oil from the engine lube pump supplies the needs of the engine lube system and the hydraulic pump for the fuel system. Oil is drawn from the sump and pressurized to lube system pressure by the lube pump. Oil flows from the lube pump through the engine oil cooler, through the oil filter, and then to the main oil gallery. A separate circuit from the main gallery directs part of the lube oil to supply the hydraulic pump. Oil flows into the inlet port of the hydraulic pump and fills the pump reservoir. The reservoir has two purposes. It provides oil to the hydraulic pump during startup until the engine lube pump can build pressure. And it provides makeup oil to the high-pressure passage in the cylinder head. When the engine is off and cools down, the oil shrinks. A check valve in the pump allows oil to be drawn from the pump reservoir to keep the high-pressure passage full. Do not remove the reservoir. The hydraulic pump is not serviceable and has no adjustments. The only serviceable components of the hydraulic pump assembly are the IAP control valve, fuel transfer pump, and pump drive gear. Oil from the reservoir flows to the inlet port of the piston pump barrel assembly. The rotation of the barrel assembly causes the pistons passing the inlet port to draw supply oil into the piston bore. The continued rotation of the barrel assembly causes the pistons to move back into the piston bore. As the pistons pass the outlet port, oil in the piston bore is pushed out of the outlet port under high pressure. This pressure ranges from 870 psi to 3,500 psi during normal operation. Oil then flows from the outlet port of the pump to the high-pressure oil supply passage in the cylinder head. The oil supply passage is actually a drilled hole which starts at the front of the cylinder head and extends through to the back of the cylinder head. This passage connects with each injector bore to supply high-pressure actuation oil to the injectors. Actuation oil from the hydraulic pump flows through the cylinder head to all of the injectors. Oil remains in the high-pressure passage until it is used by the injectors. Exhaust oil from the injectors is expelled under the valve cover and returns to the sump through the oil drain holes in the head. Now let's look at how actuation pressure is controlled. The hydraulic pump is a fixed displacement axial piston pump. The flow of this pump is directly proportional to engine speed. Minimum pump flow is at cranking speed. The pump is sized to produce adequate flow at the two most demanding conditions, hot starting and low RPM lug. During hot starting, the engine is hot and the oil is thin. In these conditions, the pump must produce 870 psi during cranking, when engine speed is only about 200 RPM. At low RPM lug conditions, the injectors are using maximum fuel at peak injection pressure. This means they require maximum actuation oil flow at peak actuation pressure. This is a very demanding requirement when the engine is only turning at about 1200 RPM. Maximum pump flow is at high idle, which is about 2640 RPM. Under most operating conditions, the pump has much more flow than it needs. This excess flow must be returned to the sump to control system pressure. The Injection Actuation Pressure Control Valve, or IAP control valve, regulates the system pressure. It returns to sump the exact amount of oil required to maintain the desired actuation pressure. Let's briefly discuss how actuation pressure is controlled. There are two types of actuation pressure. First, there is desired pressure. Desired actuation pressure is the pressure the system wants for optimum performance. The ECM determines desired pressure using software maps and inputs from many sensors. Desired pressure is constantly changing based on the sensor inputs and changing engine speed and load. Desired pressure is only constant under steady-state conditions. The second type of actuation pressure is the actual system pressure of the actuation oil powering the injectors. The IAP control valve is constantly changing the amount of pump flow returned to the sump in order to make actual pressure match desired pressure. There are three components which work together to control actuation pressure: the ECM, the IAP control valve, and the IAP sensor. The ECM determines desired pressure based on sensor inputs and software maps. The ECM sends an electrical current to the IAP control valve to change actual pressure. The IAP control valve reacts to the electrical current from the ECM by changing the pressure at which the valve returns pump flow back to the sump. This valve acts like an electrically controlled relief valve. The higher the current to the valve, the higher the relief pressure. The lower the current, the lower the relief pressure. A lack of current to the valve results in a base relief pressure of 250 to 300 psi, which is the value of the valve's spool spring. The IAP sensor tells the ECM what the actual pressure in the high-pressure passage is. The IAP sensor reads actual pressure and sends a signal voltage back to the ECM. This process repeats itself more than 60 times a second in order to make actual pressure constantly match desired pressure. This constant repetitive cycle is known as the closed-loop control cycle. It is important to understand that the system is continually working to make actual pressure match desired pressure. This means that the IAP control valve does not need a precise initial setting to work properly. Since the closed-loop control system is constantly correcting, the ECM will send whatever amount of current is necessary to the IAP control valve to make actual pressure match desired. The IAP control valve regulates actuation pressure by returning excess pump flow to the sump. High-pressure oil from the outlet port of the pump barrel assembly flows through a passage in the pump housing and onto the outlet port at the back of the pump housing. The passage to the outlet port is also connected to the IAP control valve and the overpressure relief valve. The overpressure relief valve remains inactive during normal engine operation. This simple spring-loaded relief valve only opens if a major system malfunction occurs. A major malfunction could cause actuation pressure to greatly exceed normal operating pressures. Under normal engine operation, maximum actuation pressure is 3,500 psi. The overpressure relief valve is set at 4,400 psi. This valve should never open during the life of the pump unless an excessive level of pressure occurs. You should never adjust the overpressure relief valve in the field. It's set at the factory, and raising the relief setting of this valve could cause a failure and serious personal injury. Most of the high-pressure oil flow from the pump goes to power the injectors. Excess flow is returned to the sump through the IAP control valve. Excess flow from the IAP control valve flows upward through a U-shaped tube in the pump reservoir and out a drilled passage to the front of the pump. Drain oil flows out the front of the pump, over the pump drive gear, and down the engine front gear train to the sump. The U-shaped tube acts as an anti-siphon device. It prevents oil from siphoning through the IAP control valve and emptying the reservoir during long periods when the engine is not used. The IAP control valve is an electrically controlled, pilot-operated pressure control valve. It maintains selected actuation system pressure, regardless of the engine speed, pump flow, and variable oil demand of the injectors. The basic components of the valve are the valve body, spool, spool spring, poppet, pushpin, armature, and the solenoid. The IAP control valve operates by using the variable electrical current from the ECM to create a magnetic field in the solenoid. This magnetic field acts on the iron armature and generates a mechanical force pushing the armature to the left. This force is transmitted through the pushpin to the small poppet valve. The magnetic force holding the poppet closed is opposed by reduced hydraulic pressure inside the spool chamber, trying to open the poppet. This reduced hydraulic pressure will increase until it overcomes the mechanical force of the solenoid and opens the poppet. The open poppet allows a flow path to sump for some of the reduced pressure oil. Returning part of the reduced pressure oil to the sump lowers its pressure. When the pressure of the reduced pressure oil falls below the magnetic force on the poppet closes again. With the engine off, there is no hydraulic pressure from the pump and no current to the solenoid from the ECM. The spool spring pushes the spool valve completely to the left, blocking the drain port. Approximately 870 psi, or 6 megapascals of actuation pressure are required to fire the injector during startup. To start the engine quickly, the actuation pressure must rise quickly. But pump flow is very low at startup because the hydraulic pump is being turned only at engine cranking speed. The ECM responds by sending a strong current to the IAP control valve. This holds the spool closed and blocks all flow to the sump until 870 psi is reached. At this point, the injectors fire. Once the injectors begin to fire, the ECM adjusts the current to the IAP control valve so that 870 psi is maintained until the engine starts. The ECM monitors actuation pressure through the IAP sensor, which is connected to the high-pressure oil passage. This is a closed-loop system. The ECM determines the desired pressure based on several inputs and sends a predetermined current to the IAP control valve. The ECM also compares the desired actuation pressure to the actual actuation pressure in the oil passage. It then makes adjustments to IAP control valve current to make actual pressure match desired pressure. Once the engine starts, the ECM regulates the current to the IAP control valve to maintain the desired actuation pressure. The IAP sensor monitors actual actuation pressure in the high-pressure oil supply passage in the cylinder head. The ECM compares actual actuation pressure to desired actuation pressure more than 60 times a second. If these pressures do not match, the ECM adjusts the current level to the IAP control valve to compensate. The IAP control valve allows infinitely variable control of pump outlet pressure between 870 psi and 3,500 psi. This system maintains extremely fast and accurate control of actuation pressure, providing excellent throttle response, improved fuel economy, and reduced exhaust emissions. Now let's take a few minutes to discuss how the HEUI injectors work. The HEUI injectors have 4 basic functions: to pressurize supply fuel from 65 psi to between 5,400 and 23,500 psi, to atomize the high-pressure fuel by pumping it through orifice holes in the injector tip, to deliver the correct quantity of atomized fuel into the combustion chamber, and to disperse the atomized fuel evenly throughout the combustion chamber. The HEUI injector has 5 major parts. They are the solenoid, the poppet valve, the intensifier piston and plunger, the barrel, and the nozzle assembly. The top 1/3 of the injector contains the solenoid, armature, and poppet. The solenoid is an electromagnet that creates a very strong magnetic field when energized. This magnetic field attracts the armature, which is connected to the poppet valve by an armature screw. As the armature moves toward the solenoid, it lifts the poppet valve off its lower seat. Energizing the solenoid and lifting the poppet valve off its seat is the beginning of the injection process. The poppet has 2 positions, open and closed. In the closed position, the poppet is held on its lower seat by a spring. The closed lower seat prevents high-pressure actuation oil from entering the injector. The upper seat is open and vents oil in the cavity above the intensifier piston to atmosphere through the upper portion of the injector. When the solenoid is energized, the poppet is lifted off its seat. This opens the lower seat, allowing high-pressure actuation oil to enter the injector and act on the top of the intensifier piston. The upper seat of the poppet valve closes, blocking the path to the sump and preventing actuation oil from leaking out of the injector. The center of the injector contains the intensifier piston, plunger and barrel, and plunger return spring. The intensifier piston is about 6 times larger in surface area than the plunger, providing a multiplication of force. This allows 3,500 psi of actuation oil to produce 23,500 psi of fuel injection pressure. When the poppet valve lifts off its lower seat, high-pressure actuation oil enters the injector and acts on the top of the intensifier piston. Pressure builds on top of the intensifier piston, pushing both the piston and plunger down. The downward movement of the plunger pressurizes the fuel in the plunger cavity, causing the nozzle to open and fuel delivery into the combustion chamber to begin. The barrel is the mating cylinder in which the plunger moves. The plunger and barrel together act as a pump, much like a medical syringe. Both the plunger and barrel are precision components with very small working clearances. These tight clearances are required to produce injection pressures above 20,000 psi. The barrel also contains the prime spill port. The prime spill port is a small precision hole that extends from the outside of the barrel through the side of the barrel and into the plunger. This port momentarily vents fuel injection pressure during the downward stroke of the plunger. The operation of the prime feature is fully explained in the pilot injection operation description. The bottom 1/3 of the injector is the nozzle assembly. It consists of the following components: the nozzle tip, the nozzle check, the nozzle case, and the inlet fill check ball. The nozzle assembly is similar to all other unit injectors. Fuel at injection pressure flows from the plunger cavity through a passage to the nozzle tip. Fuel flow out of the tip is stopped by the nozzle check, which covers the orifice holes in the end of the tip. The tip is held in the closed position by the force of the nozzle spring. This prevents fuel from leaking out of the tip and combustion gas from leaking into the injector when the cylinder fires. When injection pressure increases to approximately 4,500 psi, hydraulic force acting on the nozzle check overcomes the force of the nozzle spring. The pressure at which the check opens is called the valve opening pressure. Fuel flows out of the orifice holes in the end of the tip and into the combustion chamber. The check remains open and fuel continues to flow out of the tip until injection pressure drops below 4,000 psi. When pressure drops, the check closes and injection is stopped. The pressure at which the check closes is called valve closing pressure. There are 5 stages of injection with the HEUI: pre-injection, pilot injection, delay, main injection, and end of injection. Let's look now at each of the 5 injection cycles, starting with pre-injection. During pre-injection, the engine is running and the injector is in between firing cycles. All internal components have returned to their spring-loaded or non-actuated position. The solenoid is not energized, and the poppet valve is blocking high-pressure actuation oil from entering the injector. The plunger and intensifier piston are at the top of their bore, and the plunger cavity is full of fuel. Fuel pressure in the plunger cavity is the same as fuel supply pressure, approximately 65 psi. When the ECM determines that the injector should fire, it sends a current to the injector solenoid. The current causes the solenoid to produce a strong magnetic field, which creates a pull on the armature that's connected to the poppet valve by a screw. The magnetic pull of the solenoid overcomes the spring tension holding the poppet closed and raises the poppet off its seat. When the poppet valve opens, the upper poppet seat closes off the path to the sump, and the lower seat opens the poppet chamber to incoming high-pressure actuation oil. High-pressure oil flows around the poppet and into a passage to the top of the intensifier piston. High-pressure oil acting on the top of the intensifier piston forces the piston and plunger down. The downward movement of the plunger pressurizes the fuel in the plunger cavity and nozzle. When the pressure reaches the valve opening pressure, the nozzle check valve lifts off its seat and injection begins. The HEUI HEUI fuel system has a unique feature called PRIME, which is an acronym for pre-injection metering. PRIME breaks the single large injection charge into 2 separate injections. It first produces a small pilot injection. A brief delay allows the pilot injection time to start burning. The main injection is then delivered into the flame front, established by the pilot injection. The main injection immediately ignites and burns smoothly and completely. This efficient combustion significantly reduces exhaust emissions and lowers overall engine noise by up to 50%, resulting in noticeably quieter engine operation. Now, let's take a closer look at how the PRIME feature works. The plunger's downward movement produces the initial pilot injection of fuel into the combustion chamber. When the plunger groove aligns with the spill port, high-pressure fuel under the plunger can flow upward through the holes in the bottom of the plunger, out the plunger groove and spill port, and back into the fuel supply passage. This loss of high-pressure fuel causes injection pressure to drop below valve closing pressure. The spring force of the nozzle spring overcomes the hydraulic force of the reduced injection pressure, and the nozzle check closes, stopping injection. This is the end of the pilot injection and the start of the short injection delay period. As long as the injector solenoid is energized, the poppet remains open and high-pressure oil continues to flow, pushing down the intensifier piston and plunger. Main injection occurs when the plunger groove passes the spill port and injection pressure once again begins to build, opening the nozzle check. Injection continues until the solenoid is de-energized, allowing the poppet spring to close the poppet and shut off the high-pressure oil. The end of the injection cycle begins when the ECM stops the current to the injector solenoid. The magnetic field of the solenoid collapses and the poppet closes, shutting off high-pressure oil from entering the injector. As the lower seat of the poppet closes, the upper seat opens to the sump, causing the actuation oil pressure acting on the piston to drop. Fuel injection pressure under the plunger exerts an upward force on the plunger and intensifier piston. This upward force almost instantly becomes greater than the downward force on the intensifier piston, so the downward motion of the intensifier and plunger stops. When the downward travel of the plunger stops, fuel flow also stops. Injection pressure drops below valve closing pressure, and the nozzle check closes, ending injection. Exhaust oil on top of the intensifier piston can now flow to the sump through the open upper poppet seat, through the adapter, and out the adapter vent hole to the rocker arm area under the valve cover. When the nozzle check closes, injection stops and the fill cycle starts. The area above the intensifier piston cavity is open to atmospheric pressure through the upper seat of the poppet valve. The plunger return spring pushes upward on the plunger and intensifier piston, forcing oil around the upper seat of the poppet and out of the adapter vent hole. As the plunger rises, the 65 psi fuel supply pressure unseats the plunger fill check, allowing the plunger cavity to fill with fuel. The fill cycle ends when the intensifier piston is pushed to the top of its bore, the plunger cavity fills with fuel, and the inlet fill check ball returns to its seat. End of injection is now complete. This completes the description of how the HEUI mechanical components work. Now, let's discuss the low-pressure fuel system. This system has three basic functions: to supply fuel to the HEUI injectors for combustion, to supply extra fuel flow for cooling of the injectors, and to supply extra fuel flow to remove air from the system. The major components in the low-pressure fuel system are the vehicle fuel tank, the fuel filter, the fuel transfer pump, and the fuel pressure regulator. Let's take a look at how the system operates. Fuel is drawn from the tank and flows to the inlet side of the fuel transfer pump. The inlet check valve opens to allow fuel to flow into the pump, but closes to prevent fuel from flowing back out of the inlet port. Fuel flows from the inlet port in the pump to the outlet port, which also has a check valve. The outlet check opens to allow pressurized fuel to flow out, but closes to prevent fuel from flowing back through the pump. Fuel flows from the outlet port of the transfer pump to the fuel filter. The 2-micron fuel filter removes small abrasive fuel contaminants, which cause premature wear-out of the HEUI injectors. This high-efficiency filter is standard equipment on all 3100 HEUI engines. It extends fuel system life and can provide similar benefits on all other types of diesel fuel systems. This high-efficiency filter is standard equipment on all 3100 HEUI engines. It extends fuel system life and can provide similar benefits on all other types of diesel fuel systems. Fuel then flows from the fuel filter to the fuel supply passage in the head. The fuel supply passage is a drilled hole that extends from the front to the back of the cylinder head. This passage connects with each injector bore to supply fuel to the injectors. Fuel from the transfer pump flows through the cylinder head to all of the injectors. Excess fuel flows out the back of the cylinder head and into the fuel pressure regulator. Fuel from the cylinder head enters the pressure regulator and opens the 5 psi check valve. Fuel then flows through the orifice in the spring-loaded pressure control spool. This orifice allows a small amount of flow through the spool at all times to help remove air from the system and improve priming. When fuel pressure reaches 65 psi, the spool opens and spills excess flow. When the engine is off and no fuel pressure is present, the spring-loaded check closes to prevent the fuel in the cylinder head from draining back to tank. Retaining fuel in the head maintains a supply of fuel for the injectors at engine startup. 3126B engines with HEUI fuel systems will be installed in some CAT machines in the near future. These heavy-duty applications operate at a much higher duty cycle and in a much dirtier environment than truck engines. This requires a low-pressure fuel system with additional capacity to remove abrasives and water from the fuel and to provide long-hour durability under harsh operating conditions. Some or all of the following components may be found on Cat machines with 3126B powered HEUI engines. The first component is a primary fuel filter and water separator. The filter rating is typically 12 micron and removes only very large abrasives. Its purpose is to help prolong the life of the 2-micron secondary fuel filter. A water separator is also included on the bottom of the primary filter element. Next is a priming pump. The priming pump may be hand-operated or electric, depending on machine model. The primary purpose of the priming pump is to aid in removing air from the low-pressure fuel system after filter changes. This helps the engine start and run smoothly much faster. A higher capacity heavy-duty gear-type transfer pump is also used. This is the same type of pump that's used on larger engines such as the 3176, 3196, C10, C12, and 3406E. A high-efficiency 2-micron filter is now the standard filter for all applications. However, there are several different types. In applications where space is limited, the standard filter size is used. In applications where space permits and extended filter change intervals are desired, a larger capacity 2-micron filter may be used. In addition, some applications may mount the filter upside down to prevent pre-filling the filter with unfiltered fuel. That concludes the operation of the low-pressure fuel system. The 3126B engine uses a new electronic control system. This state-of-the-art system has many features and benefits, but this presentation will focus on the major electronic components that make the engine run and how they work. Basic electronic diagnostics will be covered in the diagnostics portion of this presentation. The electronic control system consists of 3 types of components: input, control, and output. Sensors constantly monitor engine operating conditions and relay that information back to the ECM. The ECM is the computer that controls the engine. It has 3 main functions. It provides power for the engine electronics. It monitors input signals from engine sensors, and it acts as a governor to control engine RPM. The ECM sends electrical currents to output devices to control engine operation. The heart of the electronic system is the new electronic control module. This powerful state-of-the-art computer controls all engine functions, providing excellent performance and fuel economy while meeting stringent new exhaust emission standards. The ECM provides many features, including full authority electronic engine control, logging of engine faults, improved electronic engine diagnostics, electronic cruise control, and programmable electronic PTO. The new ECM has 2 70-pin harness connectors, the engine harness connector and the vehicle harness connector. The engine harness connects the ECM to all of the sensors and actuators, including the HEUI injectors. The vehicle harness connects the ECM to the engine control portion of the main vehicle harness. This includes the accelerator pedal position sensor, vehicle speed sensor, transmission and brake relays, and the cruise control and PTO control switches. This wiring may seem complicated, but it's really quite simple. All of it is made up of many simple circuits. We'll cover some of these circuits in the electronic system operation portion of this presentation. Sensors are simple electronic devices that detect and convert a change in pressure, temperature, or mechanical movement into an electrical signal. There are 4 basic types of sensors: pressure, temperature, position, and speed. A pressure sensor measures changes in pressure and sends a variable DC signal voltage back to the ECM. Pressure sensors have 3 wires. The first wire supplies voltage from the ECM to the sensor, providing power for sensor operation. This supply voltage is precisely controlled to 5 plus or minus 0.5 volts. The second wire is a ground wire from the ECM to the sensor that provides a 0 volts reference. The third wire is a signal voltage from the sensor to the ECM. This signal voltage varies with changes in the pressure of whatever the sensor is monitoring. The operating range of the signal voltage is slightly greater than 0 volts and slightly less than 5 volts. A typical operating range for signal voltage is 0.5 volts to 4.5 volts. The ECM also determines if a sensor is shorted or open by monitoring the signal voltage. If the signal voltage is the same as supply voltage, the ECM knows the sensor or sensor circuit is open. If the signal voltage is 0, the ECM knows the sensor or sensor circuit is shorted. If the ECM senses either a short or an open, it will indicate a fault for that circuit to assist in troubleshooting. The key pressure sensors on the engine are the injection actuation pressure sensor and the boost pressure sensor. An atmospheric pressure sensor is used on the highest horsepower rating. An optional lube oil pressure sensor is also available for some OEM applications that require a signal for their instrument cluster. This oil pressure signal is not part of the monitoring system because it is not required for engine operation. A temperature sensor measures temperature and uses only 2 wires. Temperature sensors change resistance as temperature changes. The ECM reads the sensor's resistance value and converts it to a temperature. The ECM determines if the temperature sensor is open or shorted by monitoring the resistance value. If the sensor is shorted, the resistance value is near 0. If the sensor circuit is open, the resistance value is very high. The key temperature sensors on the engine are the coolant temperature sensor and the intake air temperature sensor. The third type of sensor is a position sensor. An example of a position sensor is the accelerator pedal position sensor. This sensor monitors the position of the vehicle accelerator pedal and converts that position into a pulse width modulated signal that is sent back to the ECM. A position sensor has 3 wires. The first wire supplies voltage from the ECM to provide power for sensor operation. This supply voltage is precisely controlled to 8 plus or minus 0.5 volts for the accelerator pedal position sensor. The second wire is a ground wire from the ECM to the sensor that provides a 0 volts reference to the sensor. The third wire is a signal voltage from the position sensor to the ECM. The accelerator pedal position sensor generates a pulse width modulated signal, which is a square wave. A square wave signal is either full voltage or 0 voltage, on or off. The percent of time the signal is on is called duty cycle. Duty cycle at the low idle accelerator pedal position is 10% to 22%. Duty cycle at the high idle accelerator pedal position is 75% to 90%. The accelerator pedal position sensor transmits this duty cycle signal to the ECM at a constant frequency. This type of sensor provides a very accurate signal to the ECM with a smooth transition during acceleration and deceleration. The ECM determines if the accelerator pedal position sensor is out of calibration by monitoring the duty cycle. If the duty cycle is less than 5% or greater than 95%, the ECM will log an active fault. The ECM determines if the accelerator pedal position sensor is faulty if the signal frequency is out of range, less than 150 Hz or greater than 1000 Hz. The fourth type of sensor is a speed sensor. This type of sensor is used for the speed and timing sensor on the engine. The speed timing sensor has a permanent magnet and a coil of wire inside. A change in the sensor's magnetic field induces a voltage into the sensor. The ECM reads this sudden increase and decrease in voltage as a signal. As the camshaft gear rotates, signal teeth cast into its rear side pass through the magnetic field of the speed timing sensor. The sensor generates a signal voltage as each timing tooth passes. The ECM counts the time between these signals to determine how fast the engine is running. All of the teeth are evenly spaced, except one pair, which has an additional tooth between them. This additional tooth sends an additional signal, which indicates top dead center to the ECM. Because speed sensors use an internal magnet and coil to generate a signal voltage, they do not require a supply voltage from the ECM. They also use only 2 wires instead of the 3 wires used on pressure and position sensors. In review, there are 4 basic types of sensors that govern engine operation: pressure sensors, temperature sensors, position sensors, and speed sensors. The electronic systems on the engine may seem complicated, but once you understand how these basic types of sensors work, the operation of individual circuits becomes much easier to understand. The speed timing circuit is the most important of all the basic circuits. This speed timing signal tells the ECM the position and speed of the engine camshaft. The ECM requires this signal to govern engine operation. The speed timing signal is so important that it has 2 sensors, a low-speed and a high-speed sensor. The low-speed sensor is more accurate at very low speeds, such as cranking. The high-speed sensor is more accurate at higher speeds and for normal engine operation. During cranking, the ECM uses the signal from the low-speed sensor until the engine starts and the idle stabilizes. After a few seconds, the ECM switches to the signal from the high-speed sensor for normal engine operation. The ECM will continue to use the high-speed sensor until the engine is shut off. If the ECM detects an open, short, or faulty signal from either sensor, it will automatically switch to the other sensor. During the switch, the engine may have a momentary misfire, but it will quickly resume normal operation. The ECM will continue to use the backup sensor, and it will indicate both an active and a logged fault. The ECM will delay lighting the check engine light after detecting a sensor failure, because the engine will continue to operate without loss of performance. But the ECM does immediately indicate the fault, so the service technician can find and repair the problem. A significant performance benefit of the HEUI system is that it can produce any desired injection pressure at any engine speed or operating condition. This is accomplished by controlling the injection oil actuation pressure that powers the injectors. In the HEUI system, fuel injection pressure is about 6 times greater than actuation oil pressure. At idle and very light load conditions, a low injection pressure is used to reduce combustion noise and exhaust emissions. At rated horsepower or full load conditions, a very high injection pressure provides the best performance and lowest exhaust emissions. The injection actuation pressure control circuit controls the operation of the IAP control valve and the actuation oil pressure that operates the HEUI injectors. The ECM determines the desired actuation pressure based on input from the accelerator pedal position sensor and other engine sensors. The ECM then uses software maps programmed into the ECM personality module to determine the desired actuation pressure. The ECM then calculates the correct amount of control current to send to the IAP control valve to produce the desired pressure. The IAP control valve responds to the control current and regulates actual system pressure. The IAP sensor constantly monitors actual system pressure and converts the pressure into a DC signal voltage that's sent back to the ECM. The ECM compares actual pressure to desired pressure. If actual pressure is higher or lower than desired pressure, the ECM will adjust the control current to the IAP control valve to try to make actual and desired pressure match. This cycle of determining desired pressure, sending current to the IAP control valve, reading actual system pressure and adjusting control current, repeats itself more than 60 times a second. This is called a closed-loop circuit and provides very rapid response and precise control of injection actuation pressure. The accelerator pedal position sensor circuit determines desired engine speed by sensing the position of the accelerator pedal and sending a pulse width modulated signal back to the ECM. The ECM then compares desired engine speed to actual engine speed and determines how the injectors should be fired. Here's how the circuit works. The operator selects an engine speed with the accelerator pedal. The position of the accelerator pedal is translated into a pulse width modulated signal to the ECM. The duty cycle of the signal is translated by the ECM into a desired engine speed. The ECM then compares desired engine speed to actual speed and determines if the injectors should deliver more or less fuel. If actual engine speed is lower than desired, the ECM will increase current duration to the injectors to deliver more fuel and increase engine speed. If actual engine speed is higher than desired, the ECM will decrease current duration to reduce fuel delivery. With less fuel, engine speed drops very rapidly until actual engine speed matches desired speed. The ECM uses many other sensor inputs besides the accelerator pedal position signal to determine the correct operation of the HEUI injectors. The ECM must determine three things to control injector operation: injection timing, which is when injection starts; fuel quantity, which is the amount of fuel injected; and injection pressure, which is the rate at which fuel is injected. All of the sensor inputs are compared to the software maps in the ECM, and output signals are sent to the injectors and IAP control valve. These two output signals control actual engine operation. The boost sensor measures boost pressure in the intake manifold. It's a pressure sensor that sends a DC signal voltage back to the ECM. The ECM uses the boost pressure signal to limit fuel delivery and prevent overfueling and black smoke. The atmospheric pressure sensor measures atmospheric pressure in order to compensate for altitude. It sends a DC signal voltage back to the ECM. The ECM uses the atmospheric pressure signal to adjust timing and fuel delivery to maintain engine performance and emissions at high altitudes. This sensor is not used at lower horsepower ratings, so it will not be on all engines. The coolant temperature sensor measures the temperature of the engine coolant. It converts temperature into a resistance value that the ECM reads. The ECM uses the coolant temperature signal to help determine proper injection timing and engage or disengage the intake air heater during cold weather operation. The intake air heater warms cold intake air, improving cold idle quality and significantly reducing white smoke during engine warm-up. The intake air temperature sensor measures the temperature of the air entering the intake manifold. It converts temperature to a resistance value that the ECM reads. The ECM uses the intake air temperature signal
to help determine proper injection timing and engage or disengage the intake air heater during cold weather operation. The intake air heater warms cold intake air, improving cold idle quality and significantly reducing white smoke during engine warm-up.
Understanding the basics of how the fuel and electronic control systems operate is essential to identifying system problems. The objective of this section is to introduce the basic diagnostic procedures used to identify and correct problems on HEUI-powered engines. The system used in this presentation is only an example of a typical modern HEUI system. Sometimes when the serviceman receives complaints about problems such as low power, poor fuel economy, or poor idle quality, its source is unwarranted customer expectations rather than an actual engine problem. Now that we've seen the basics of how the fuel and electronic control systems should operate, we will discuss how to identify system problems. The objective of this section is to introduce the basic diagnostic procedures used on the 3126B. Modern, electronically controlled engines offer improved diagnostic capability over older mechanically controlled engines, but they are not totally self-diagnostic. In order to effectively troubleshoot an electronic engine, servicemen must have 5 skills. They must be able to understand how the fuel system and electronic control systems operate, find appropriate information in the Caterpillar service manual, perform basic mechanical tests, perform electronic system tests, and interpret test results to find the root cause of a problem. A good basic understanding of system operation is the most important part of effective troubleshooting. For example, adjustments to horsepower or performance characteristics are made by installing new software or by upgrading mechanical components. No mechanical adjustments can be made to any part of the HEUI fuel system. Servicemen who do not understand how components and systems operate end up guessing at which component to replace. Replacing the wrong component increases customer downtime, repair cost, and customer dissatisfaction. In addition, never disassemble HEUI fuel system components in the field. Disassembly generates thread debris and introduces dirt, causing serious injector damage. Unauthorized disassembly of warranty components will result in reduced or non-allowed warranty reimbursement. A second important skill is the ability to use the Caterpillar service manual effectively. The service manual has 3 parts: engine, troubleshooting, and maintenance. Under the Engine tab, you will find 3 modules: Specifications, Systems Operation, Testing and Adjusting, and Disassembly and Assembly. In the Specifications module, you will find torque values, torque sequences, pressure settings, and numerical values for adjustments, such as valve lash settings. In the Systems Operation, Testing and Adjusting module, you will find explanations of how mechanical systems operate, test procedures for mechanical components, and adjustment procedures for mechanical components such as the valve lash settings. In the Disassembly and Assembly module, you will find removal and installation procedures for major components, such as HEUI injectors, disassembly and assembly procedures for serviceable components like water pumps, and disassembly and assembly procedures for the basic engine. Under the Troubleshooting tab, you will find an electrical schematic and a troubleshooting module. The schematic contains location and identification information for engine wiring, connectors, electrical components such as switches and relays, and electronic components such as sensors and the ECM. The Troubleshooting module contains all of the information for troubleshooting electronic engines. Topics that are covered are troubleshooting, electronic system overview, programming parameters, troubleshooting without a diagnostic code, troubleshooting with a diagnostic code, and a diagnostic code list. In the Operation and Maintenance Guide, you will find maintenance information that is primarily intended for the operator or owner. This guide contains specifications for cooling, lube and fuel systems, recommended practices for engine operation, and maintenance recommendations such as maintenance schedules and refill capacities. The next important skill is to be able to perform basic mechanical tests correctly. This includes being able to measure hydraulic pressure, use a volt-ohm meter to perform basic electrical tests, checking boost pressure and exhaust restriction to determine if the engine performs properly. It is also essential that you use and understand the features in Caterpillar Electronic Technician, or ET for short. ET is required to service electronic engines. With it, you can identify, understand, and correct active faults, logged faults, and logged events. You can also read and change programmable parameters and view status screens. You can perform the injector solenoid test, the injection actuation pressure test, the cylinder cutout test, and several other special tests that enable and disable specific ECM outputs. In order to better understand these basic tests, the solenoid test, the injection actuation pressure test, and the cylinder cutout test are performed and explained in the diagnostic section of this presentation. Finally, interpreting test results to find the root cause of a problem is critical. This includes being able to evaluate component performance of the sensors, actuators, injectors, and associated wiring. It also includes being able to understand how components and systems interact, how components work correctly, and how the system reacts if a component is faulty. These skills are important to be able to quickly identify and correct problems on electronically controlled engines. Only electronically controlled engines constantly meet demands for improved performance, reduced emissions, and improved fuel economy. There are many misconceptions about what electronically controlled engines can and cannot do. A quick review of these will illustrate why the troubleshooting skills just mentioned are so important. Electronically controlled engines can indicate active faults, log faults, and events, identify major component failure, and identify sensor and actuator short and open circuits. Electronically controlled engines cannot troubleshoot themselves, identify marginal component performance, or identify all inaccurate sensor readings. In short, electronically controlled engines cannot think for themselves. It is your ability to think and understand how engine components and systems work together that allows you to perform effective troubleshooting. Performing the basic electronic tests on HEUI engines is simple. The electronic diagnostic tool used to perform these tests is the Caterpillar Electronic Technician, or ET for short. ET is actually a software package run on a laptop computer. ET can perform the injector solenoid test, the injection actuation pressure test, the cylinder cutout test, identify active faults, logged faults, and logged events. ET can display engine configuration, change customer programmable parameters, flash program new software into electronic engines, and print configuration and test results for further analysis. Prior to flash programming, older electronic engines were equipped with replaceable personality modules. Installing new software required ordering and installing a new personality module. This method increased both product cost and customer downtime. Newer ECM designs contain an integral personality module, which is not replaceable but can be flash programmed. ET is required to flash program both new and older engines. This presentation uses ET to demonstrate the basic electronic tests with the screens and cursor commands to perform each test. It does not cover the actual instructions on how to use ET. Specific instructions are available in the Caterpillar Service Tool Software User's Manual for Cat Electronic Technician, form number NEHS 0679.
The first diagnostic test identifies active fault codes, or active faults for short. Active faults are faults which are currently present and indicate a system malfunction or problem. An example is a shorted or open sensor, wire, or circuit. Let's look at an example. When no active faults are present, the ET screen will read "No active codes." If we unplug the injection actuation pressure sensor harness connector, ET identifies this as an open circuit active fault after a few seconds. The ET numerical code for this fault is 164-3, and ET defines this fault as an injection actuation pressure sensor open circuit. Detailed information for troubleshooting this code is listed in the troubleshooting guide.
Logged faults are faults which are not currently present, but have previously occurred. When logged faults are not present, the ET screen reads "No logged diagnostic codes." Here, the injection actuation pressure sensor open circuit fault has occurred 10 times. The first occurrence was at 3 hours, and the last occurrence was at 27 hours. The diagnostic clock indicates the total number of hours on the engine, in this case 27 hours. The ECM can remember up to 256 occurrences of a logged fault. If the fault occurs more than this, the ECM will remember the last 256 occurrences. However, after 100 hours, most logged codes are deleted.
Now let's look at examples of logged events. Logged events are generally not electronic problems, but they do indicate an abnormal engine condition. Examples of logged events are a programmed idle shutdown occurrence, engine overheat, or engine overspeed. These are not electronic problems but are abnormal operating conditions. Now let's look at the injection solenoid circuit test. The purpose of this test is to make sure that there are no open or short circuits in the injector wiring harness and that all of the injector solenoids are working. To start the test, select the Start button at the bottom of the screen. ET will then instruct the ECM to actuate each injector solenoid in order from 1 through 6. This test will continue until the Stop button is activated at the bottom of the screen. If an open or short circuit is detected, the fault will be listed on the screen, and the defective circuit will not work.
Now let's look at the injection actuation pressure test. The purpose of this test is to determine if the pump can produce maximum pressure, if the IAP control valve is working properly, if the pump is worn, or if there is a leak in the system. The actuation pressure test evaluates the condition of the hydraulic system by asking the pump and IAP control valve to produce 4 different system pressures at idle speed. If the pump and valve can produce and control the pressures, the system is working properly. The 4 different pressures are approximately 870 psi, 1400 psi, 2100 psi, and 3300 psi. This test considers 3 primary criteria: injection actuation pressure, which is the actual system pressure; the injection actuation output, which is the percent of control current on time to the IAP control valve; and finally, desired injection actuation, which is the desired system pressure determined by the ECM. Now let's look at the ET screen before the test starts. With the engine off, actual pressure is 0 and current to the IAP control valve is 0. Desired pressure is about 870 psi. When we start the test, you will hear the sound of an actual engine running during the different phases of the test. This engine is running normally and illustrates both the expected noise and variability of a properly running engine. Now let's start the engine and listen to what it sounds like at idle for a few seconds. When running the IAP test, it's important that the engine be at full operating temperature and at low idle. Performing tests below normal operation temperature or at any speed other than low idle will cause test results to be inaccurate and unrepeatable. When we start the engine, the test starts at normal idle conditions. Desired pressure is approximately 870 psi, and the IAP CV control current is usually in a range of approximately 10% to 22%. Actual pressure should be in a range of approximately plus or minus 100 psi of desired pressure. The actual pressure reading may seem erratic, but that's largely due to the slow firing frequency of the injectors at idle speed and the data sampling rate of the ET. The low idle speed is necessary to make sure pump output flow is at a minimum, so that internal pump wear or system leakage shows up. Next, select the Step Up button. The ET tells the ECM to increase desired pressure to about 1400 psi. Actual pressure should be in a range of about plus or minus 100 psi of desired pressure. Pressing the Step Up button again will increase desired pressure to about 2100. Again, actual pressure should be in a range of about plus or minus 100 psi of desired pressure. Pressing the Step Up button one more time increases desired pressure to the maximum operating pressure of about 3300 psi, and actual pressure should be in a range of about plus or minus 100 psi of desired pressure. Control current output should be 65% or less. If the IAP CV control current is 65% or less, the system is operating normally. If controlled current is greater than 65%, the pump may be worn, or there may be a leak in the system. If controlled current varies more than plus or minus 2%, or if actuation pressure is erratic, the injection actuation pressure control valve may not be operating properly. Refer to the troubleshooting guide for specific instructions if any of these readings indicates a problem. When the Step Down button is selected, ET tells the ECM to go to an intermediate pressure of about 2100 psi. Here we're just looking to see if actual pressure matches desired pressure in order to verify the IAP control valve is working properly. We're not concerned with the IAP CV control current. If actual pressure does not match desired or is very erratic, the valve may not be operating properly. As you continue to step down pressure to the starting pressure of 870 psi, actual pressure should remain within 100 psi of desired pressure. In summary, the purpose of the injection actuation pressure test is to determine if the pump can produce maximum pressure, if the IAP control valve is working properly, or if the pump is worn or there is a leak in the system. Remember, if the actuation test shows that the system cannot produce maximum pressure, it does not necessarily mean the pump or IAP control valve are defective. It may be a leak somewhere in the actuation circuit. Before replacing a pump or control valve, always make sure there is not excessive leakage from one of the injector vent holes or from around the injector high-pressure seals in the cylinder head. This is done by disabling the injectors so that the engine will not start, and cranking the engine while visually observing leakage. Refer to the troubleshooting guide for specific instructions on this procedure. When the actuation pressure test indicates that maximum actuation pressure is low, a pump deadhead test must be performed to determine if the problem is in the actuation circuit or the pump. The deadhead pump test isolates the pump and the IAP control valve from the rest of the circuit. It also tests the condition of the pump and the IAP control valve. This pump test is very simple to perform. First, disconnect the high-pressure oil line from the back of the hydraulic pump. Next, install a 5,000 psi or greater pressure gauge. Then crank the engine until the maximum pressure is reached on the gauge. This should not take more than 3 seconds. This test causes the pump to go to the relief pressure setting of the overpressure relief valve. The normal range for this relief setting is about 4,300 psi. If pressure is less than 4,000 psi, replace the IAP control valve and repeat the test. If pressure is still below 4,000 psi, replace the pump. If pressure is 4,000 psi or more, the pump and valve are operating properly. Check for leakage from the injector vent holes or high-pressure seals. This is done by disabling the injectors so that the engine will not start, and cranking the engine while visually observing leakage. Refer to the troubleshooting guide for specific instructions on this procedure. When performing this test, always use a recently calibrated gauge to ensure test accuracy. Now, let's look at the cylinder cutout test. The purpose of this test is to determine if all cylinders are firing evenly and is the best indicator of individual injector performance. The cylinder cutout test measures the contribution of individual cylinders, compares one to another, and determines if any are weak. The cylinder cutout test menu in ET version 2.4 and later has 2 different test options. First is the manual cylinder cutout test. This option allows the service technician to select and cut out individual cylinders. The manual test option is normally used to compare one cylinder to another without running through the entire automated test procedure. The preferred option is the automated cutout test, which is recommended for most applications. This option automatically tests all 6 cylinders 3 different times and averages the results for each cylinder to reduce test variability. It then calculates individual injector performance and identifies injectors as OK or not OK. The test strategy for HEUI engines is different from the automated multiple cylinder strategy used on HEUI engines. On mechanically actuated fuel systems, plunger speed and pumping rate are directly proportional to crankshaft speed. Because plunger speed is fixed, fuel delivery into the cylinder decreases as injector internal leakage increases. Leakage increases with increased engine load and fuel delivery. Engine load and injector leakage can be increased by cutting out multiple cylinders. This strategy makes weak cylinders easier to identify. The HEUI test strategy is different because HEUI injector operation is fundamentally different than mechanically actuated HEUI. The plunger speed and pumping rate of the HEUI injector are not determined by crankshaft speed. The force of the actuation oil pressure on top of the intensifier piston accelerates the plunger and increases pumping rate. The plunger is slowed down by the force of fuel injection pressure under the plunger opposing actuation pressure on top of the intensifier piston. These opposing forces achieve a force balance during injection. As plunger leakage increases, fuel injection pressure drops. The actuation pressure will then cause the plunger to move farther and faster to make up for the leakage to achieve a force balance. This means that the HEUI self-compensates for wear and provides very stable fuel delivery as the injector wears. There are 2 conditions where HEUI injector wear and leakage can be identified: low idle and peak torque fuel delivery. At idle, fuel delivery is so small and injection duration so short that a worn plunger cannot accelerate fast enough to compensate. At maximum fuel delivery, a worn plunger will simply run out of stroke before it can compensate for leakage. However, this requires the engine to be run at full load It cannot be simulated using multiple cylinder cutout, as with HEUI. Since a chassis dynamometer is required to achieve full load, the most common test condition is no load, low idle. However, low idle fuel delivery has a good deal of variability because this is where the smallest amount of fuel is being delivered and is the most difficult condition for the fuel system to govern. That is why the automated test repeats the test for each cylinder 3 times and averages the results. After all of the cylinders have been tested and averaged, ET calculates system average and compares individual cylinder values to the system average. Injectors with readings above or below factory specifications that are identified by ET as not OK may be defective and need to be replaced. However, not OK readings may not be the result of worn or faulty injectors. Injectors are often replaced when the cause of the problem was a loose or burned harness connection, low cylinder compression, a burned intake or exhaust valve, or other mechanical problem. The new cutout test also has some new parameters to increase test accuracy. For the test to work properly, warm the engine to a normal operating temperature. The new automated cylinder cutout will not allow the test to start if the coolant temperature is below 171 degrees Fahrenheit. The second new parameter is engine speed during the test. The test is run at programmed low idle speed. If engine speed is manually changed to other than programmed low idle, the test will not start or will abort if in progress. Accessories that put an intermittent load on the engine should be disabled during the test. Air compressors and air conditioning compressors, which can cycle on and off, will add to test variability if they cycle on and off during the test. ECM-controlled cooling fans are turned on and left on throughout the entire test. Let's take a look at how the test works. Select the Start button to start the test. The automated cylinder cutout test begins at programmed low idle speed. If programmed low idle is above or below the range specified on the ET screen, the technician must set engine speed to the requirement stated on the ET screen. Once selected, this speed is maintained throughout the test. If it is changed, the test will abort. The ET software then turns off one injector at a time. The remaining 5 cylinders must then produce more power to maintain the selected idle speed. After the idle has stabilized, the ECM measures the average duty cycle of the solenoid current to the 5 working injectors. The ECM then assigns a test value to the injector being tested. This cycle automatically repeats for each injector. Let's take a few seconds to listen to the sound of a test on a properly operating engine. Once all 6 cylinders have been checked, the test is complete. Each cylinder is defined as OK or not OK. There are no exact specifications for these test values because many variables cause each engine to be somewhat different. These variables include oil viscosity, oil temperature, parasitic load, fuel quality, altitude, engine, and component wear condition, and many others. What is important is the relative difference between the test values from cylinder to cylinder on a given engine. In order to reduce test variability and make it more accurate, the test repeats 3 times and the results are averaged. Once all 6 cylinders have been checked 3 times each, test values are assigned to each cylinder. The ET software completes the calculation and identifies which injectors are OK or not OK. Individual test readings can be viewed by selecting the Show Details button. These values are calculated using actuation pressure and current duty cycle to simulate a hypothetical mechanical rack position in millimeters of rack. These values do not accurately correlate to an actual rack measurement, but may be useful to compare one cylinder to another. They also include test variables as well as normal injector-to-injector delivery variability. ET uses these values to compare each cylinder to the system average and make an OK or not OK determination. Under the Diagnostics, Diagnostic Test, Special Tests menu, there are up to 14 additional tests. These tests are used to actuate specific ECM outputs to determine if the ECM is working properly. A few examples of these tests include cooling fan on-off. This turns the cooling fan ECM output on and off. PTO switch on lamp. This turns the PTO lamp on and off. Tachometer test. This sets the tachometer to 1500 RPM. 55 miles per hour speedometer test. This sets the speedometer to 55 miles per hour. The technician is instructed to connect one lead of a test lamp to the ECM output and the other lead to battery positive or ground. The ECM output then powers the test lamp. Caution: a multimeter cannot be used in place of a test lamp. The ECM output must drive a load, such as a lamp. This completes our discussion of basic diagnostic tests. A review of the most common customer complaints reveals the actual cause of the problem. Most injectors replaced under warranty are returned to the factory to determine the cause of failure. The process used to evaluate returned injectors is warranty analysis. This process consists of 3 major steps. The first step is a complete visual inspection. This inspection looks for signs of external damage caused by the following problems: burned solenoid terminals from loose connections, injector tip or nozzle case damage from engine overheat or improper assembly, rust or signs of water ingestion from the fuel supply, damage from improper injector removal, parts handling, or return shipment. The next step is a thorough injector performance analysis. This includes running the injector on a performance test bench at both idle and rated speed and fuel deliveries. These tests are longer and more demanding than the original production performance test. This ensures that the injector actually operates correctly under all operating conditions. The final step is a teardown analysis on any injector that does not pass all visual and performance test standards. Parts are inspected for defects using the most modern inspection equipment available. This includes microscopes, electronic roundness and surface finish machines, and even a scanning electron microscope where necessary. This equipment is capable of finding even microscopic flaws and defects. In fact, the scanning electron microscope can magnify the surface of an object up to 20,000 times. It is used to identify inclusions that cause failures and locate the origin of cracks. Here, a sulfide inclusion in a piece of material is shown at various magnifications. In order to preserve evidence of a failure, it's very important that the failed pieces be returned exactly as they were found. If you are ever requested to return failed parts to the factory for analysis, do not clean the pieces or put them back together. Cleaning or reassembling the fracture surfaces destroys evidence, which can pinpoint the failure. Wrap the pieces individually in soft paper towels and return them in the same box or envelope clearly marked for identification. Results from the performance, teardown, and failure analysis are compiled and reviewed by both engine and fuel system engineers to determine root cause of problems and necessary corrective action. Problem resolution teams address emerging problems where corrective action is unknown. Let's look at some of the most common customer complaints listed on warranty claims and their actual root cause. The top 3 customer complaint categories comprise over 95% of all HEUI injector warranty claims. They are misfire, no information, and runs rough. Each of the above complaints is a description of the problem. Just a few root causes are responsible for most of the complaints. Misfire or dead cylinder is the most common complaint. There are several possible causes for this complaint, but 2 account for nearly all complaints. Burned solenoid terminals from a loose harness connection is by far the largest cause of misfire. If an injector must be replaced due to burned connector pins, be sure to also replace the harness connector. The second cause, which is much less frequent, is debris damage to the injector poppet. This typically occurs on new engines where debris such as core sand, cast iron nodules, or machining chips dislodge during operation and pass through the poppet seat. These large abrasive particles may damage the poppet seat, cause poppet leakage, and reduced injector delivery. In extreme cases where the debris is very large, it may become lodged between the poppet and seat, holding the poppet open. This will result in a dead cylinder and a large actuation pressure leak. This leak may be large enough to prevent the engine from starting. The second most common cause of misfire is no fault. This means that the injector had no visual defects and passed all factory performance tests. In short, the injector had no defects and did not require replacement. The automated multiple cylinder cutout test should help this problem because it positively identifies which injectors are acceptable. However, there are a few things which the service technician should look for when diagnosing a misfire complaint. In addition to inspecting the injector solenoid connection, perform a visual inspection and pull test of injector harness wiring and connections. This is especially important if the problem is intermittent. Problems which are intermittent are generally a poor connection rather than a mechanical failure in the injector. Poor connections often generate repeat warranty claims. The vast majority of HEUI injectors replaced as dead were actually loose or poor connections. Warning: inspect electrical connections only with the engine off to avoid risk of personal injury. No information is the second most common complaint category. On many low-dollar claims, a claim story is not required. On these claims, injectors are analyzed, but there's no specific customer complaint listed. There are several root causes of problems in this category. More than 1/4 of all defects were due to ingestion of large amounts of water in the fuel. This results in damage to the injector plunger and leads to eventual failure. The next most common cause is combustion gas leakage between the injector case and cylinder head. This allows combustion gas to leak into the fuel supply passage and cause misfire or rough running. It's often caused by low torque on the injector hold-down clamp and is not an injector defect. If you see any sign of leakage at the combustion sealing band, clean the injector case and combustion seat and reinstall the injector. The remaining categories are injector failures caused by internal defects or engine debris. All of these causes have been identified and corrected or are being actively worked on by a problem correction team. The final major category is rough running. This complaint is sometimes difficult to diagnose because there are many potential causes. In addition, one or more injectors may be weak, but not dead, and the misfire is often intermittent. The automated cutout test should make identification of weak injectors much easier. However, if the cutout test cannot identify the problem, it may be necessary to manually shut off cylinders one at a time to determine if an injector is weak or the problem is intermittent. If you cannot pinpoint the cause of low power or rough running, check fuel pressure. The most common cause of poor performance is a plugged fuel filter. If this is not the cause, a PAR dyno test is recommended for on-highway trucks. It is also important to note whether the complaint is recent or whether it has existed since the engine was new. Performance complaints on new engines are often the result of unreasonable performance expectations, incorrect truck drivetrain specification, or machine misapplication. In some cases, the performance of multiple injectors or the entire injector set degrades. In this case, it's usually difficult to clearly identify a single weak injector. There is no manufacturing or mechanical defect that affects an entire injector set. Degradation of an injector set is usually caused by an excessive amount of water or abrasives in the fuel, which causes plunger wear damage and excessive leakage. The use and maintenance of water separators and Caterpillar high-efficiency filters can help prevent water damage and premature wear from abrasives in the fuel. In rare instances, rough running may be caused by poppet damage from debris in the oil. This usually appears as a loss of power on one cylinder. Damage to the poppet seat results in leakage of actuation oil, resulting in low fuel delivery on the affected cylinder. All known injector failure modes combined account for about 3/4 of all returned injectors. This demonstrates a significant improvement in dealer diagnostics over the past several years, when no faults accounted for about 2/3 of all returns. Resolution teams are actively working to or have already resolved all injector failure modes. In addition to improved injector design, you will see a rapid evolution in fuel filtration across the product line. No faults account for about 1/4 of all injectors returned. This category represents our biggest opportunity to reduce warranty claims and improve customer satisfaction through improved diagnostics. This is the driving factor behind the automated multiple cylinder cutout test and the development of improved training methods such as this presentation. You can help reduce no faults by looking for external causes of misfire, low power, or rough running. These include checking injector connections and wiring for clean, solid contact, checking inlet and exhaust systems for restriction, checking fuel supply pressure to assure that pressure is adequate and the secondary fuel filter is not plugged. Finally, make sure customer expectations are reasonable. Some customers have expectations for smoothness, economy, or performance, which are simply beyond the capability of an engine or fuel system. In these cases, replacing injectors as defective is counterproductive because it reinforces the customer's impression that the parts were actually defective. This concludes the introduction to fuel system operation and troubleshooting of the HEUI HEUI fuel system. Understanding how the fuel system operates, how to perform basic diagnostic tests, and where to find service information will help you improve reliability and make it easier to troubleshoot and repair HEUI fuel systems.